So since this is a lightning demo, I didn't really prepare much of anything, but as it turns out, I'm going to talk about Dask, and it turns out that their introduction is actually pretty good for giving a pretty good overview, so I don't really need to prepare that much anyway. So what Dask is a flexible parallel computing library for analytic computing, which is what it says in the tagline there. But essentially what it does is it enables you to run like really big jobs that won't fit in memory, like a chunk at a time, so that you don't have to do, buy a really big expensive computer or something like that. But also you have some flexibility where you can also run, you can run it on multiple computers as like a parallel job manager kind of thing, but you write just the one line or whatever stuff. So I'm going to skip all of that stuff and just look at what it looks like. There are basically the three different types of data sets you can use with Dask. So there's an array, which works kind of like NumPy. There's a bag, which is like random objects in Python or something like that, or like dictionaries and things. And then there's a data frame, which is kind of similar to Pandas data frame. And then you write your lines of code, which is generally essentially the same as writing Pandas or NumPy stuff, and it becomes a graph, which is sort of like, here are the steps to do what I want to do, but don't actually do them yet. So then that way you can say, here's a bunch of data, and here's the steps I want to do. And then Dask will do that and chunk all the data into separate sections and do those operations on the sections one at a time or in parallel or whatever. And then that way you don't have to use everything all in memory at once, that kind of stuff. And then their schedulers means that you could run it all just in order, or you can run it in parallel, or you can run it on like a cluster or something like that. So the example is pretty straightforward. If you look at what it looks like in comparing Pandas to the Dask data frame, you see in Pandas, you might want to read your CSV file here, and then do some kind of group by something, and then you take the mean of that. In Dask, it's pretty similar. You import dask.dataframe instead, and then you use read CSV, which is the same function, and then you do exactly the same operation. The only difference is at the very end you say compute, because all of this stuff before to the Dask data frame is just saying this is what the operations I want to do in parallel, but they haven't actually been done yet. And a similar thing happens with NumPy. So say, for example, you're reading a really large HDF5 file into a NumPy array, and then you take the mean of that along some axis. You can do the same thing in Dask, where you read the file again, where you say, give me a Dask array from that data you have in the HDF5 file, and also split it up into chunks that are 1,000 by 1,000 in each dimension. So that way, you, instead of saying load the entire thing, you say we want to load chunks that are 1 million elements long and work on them, each chunk individually. So this x.mean will just say, instead of actually taking the mean, it'll say, I want to do the operation of taking the mean on every single chunk and put it all together. And then when you call compute on that, it will actually do that computation and calculate the mean for every single chunk. Yep.
In the previous example, would it parallelize it to another code? Like, you don't have to say what the chunk size is?
So the previous example, it basically cuts it by index. So it'll cut the rows into some reasonable thing. I think in this case, because there's a bunch of CSV files, I think it cuts it by every CSV file. So that's basically how that one works. But, I mean, you could pass some additional parameters there. You cut the chunks or cut the index in the specific point or whatever. And then the bag is the one that does random stuff. So in this case, it's trying to work on a JSON file. But I don't really use that, so I'm going to not really explain much of that. And then one last thing is a sort of delayed thing, which is kind of like if you look at the vectorize function in NumPy, which says, if you have a function that takes one input element and gives you one output element, then the vectorize function will optimize it so that you can run that on like a whole array, as opposed to doing a for loop over every single element. It will do that for loop in C or whatever. So the delayed function in Dask does a similar thing, except it says record that I want to run the load function on this value fn, and record that I want to run this process function on the data that was a result of that, and keep it in this list. And then record that I want to run the summarize function on that list of results. And so as a direct thing, you would basically just be looping to the thing, loading the file, processing it, and then calculating a summary of the list that you had. But what Dask will do is it can parallelize it. So now it knows that when it's got the summarize function, it's inputting, 10 items of files, and it can see that the load and the process are not related to each other, so it can run those in parallel instead of doing a for loop and doing iteratively one file name at a time. It says, oh, well, the summarize is taking a bunch of things and give me one thing. So I can calculate all those inputs separately without waiting for the first one to be finished to get to the second one and that kind of stuff. So basically, yeah, and for this case, it's parallelize it for you because it's actually going to be running in parallel, not just vectorized. So pretty much, yeah, you can run it with anything. So I mean, if you're not going to end up with a list of things, though, it's not really going to do much help because it's not really going to parallelize anything, right? I mean, the point is that you have to have independent parts in this for loop, right? Otherwise, right? Yes. So the example I want to look at is, I don't know, inspecting. So you can kind of see how it, well, I'm not going to go into the details of it, but if you look at here, the Dask array API is very similar to NumPy. So you can use, instead of NumPy.1s, you can use Dask array.1s. You say 5 by 15, but the additional thing is you say how you want the chunks to be split up. So you want it to be split up in 5 by 5 chunks. And so when you look at the Dask attribute, that gives you sort of an overview of what Dask sees as the chunks and everything there. So the values don't really matter, but with it, you can actually see how it's working. So in here, you can see how we wrapped the ones function 3 times, and then we have an x+1 function that does an add and whatever on the wrap function and adds 1 to it. It's not really a big deal, but the interesting thing is really the visualization, which shows you how you can see how it's parallelized, is that you've got 3 chunks, and then it calls this function f, and then it calls wrapped, and then it comes to 1. So actually, I got that backwards. You started with 1s, you split it out into 3 chunks wrapped, 1, 0, and 2. I don't know why it's not in the same order, but anyway, 0, 1, and 2. You call f on it, and then you have your result x2 that came out of that. So you can sort of see how Dask saves a graph of what to do, and it doesn't actually do the work until you say compute. And then when you say compute, it will go and look at all the parallel trees along that graph and say, well, these things are independent, so I can run on that, and then I can run on the other side at the same time, and I don't have to wait for it. And then when everything comes together, somewhere it says, okay, well, here I'm going to wait for all the other branches or whatever like that. Anyway, you can look at the example for arrays. So I think the overview is good enough. So like I was saying, you basically, instead of having a NumPy array, you have a bunch of smaller NumPy arrays in chunks. And so Dask will say, well, I'm going to operate on this entire thing. But when you told me to add 1, I will only calculate, say, the chunk for this thing on one processor and the chunk for this thing at another processor, etc. Anyway, since this is a lightning demo, I don't really have anything more to say about it. I'm just saying that's how it works. It basically has it allows you to split up your computation into separate chunks, and then you can say, do a bunch of stuff, but it doesn't actually do it. And then at the end, you say compute, and it'll run all the stuff in parallel, and then you have, hopefully, a result that you don't have to use all the memory, or you can use it in parallel or something like that.
So whatever you're trying to do has to be parallelizable at some point.
Right. In some way, I mean, it has to have some kind of parallelized thing, right? Like an array could be parallelized in chunks or whatever if you're doing like summing things or taking the mean or whatever. Right, like if you're doing something where, you know, the first element feeds into the second element and feeds into the third element or something like that, or like a recursive kind of thing like that, then you couldn't necessarily do it unless you could rewrite it in a way that everything is independent. There are ways to write it so that if you're doing like finite difference or something where you need to access one next to it or something like that, you can add ghost points to the chunks. So it's not limited to the fact that as long as you've got a local area that one point depends on, then it still works. But I mean, if one point depends on every single previous point, then you can't really, or every single point to the left and to the right or something like that, you can't really parallelize it. But if it only requires a local area, like say 3 next to each other, if you're doing like a Gaussian blurring or something, then you can add some ghost points around every chunk, and they can access like the next door chunk to have it work.
So as soon as I have like a group operation, it takes more than 30 seconds.
You could try that. So group by, so the one thing about data frames is it's not the full pandas interface, because pandas interface is gigantic, but I think the overview has a list of some reasonable things. So like I was saying, it splits it up by like index, so you know you can split it up by month or something, or you can split it up by timestamp or whatever, depending on what your index is on your data frame. So I mean, the API is basically the same. You can do like head, and you can access one element where it equals something else and add whatever, and then it will work. But of course, some things you just can't do in parallel, like it says, right? So, but a lot of things that you would do that are straightforward are basically doable. So element-wise operations, selections, subsetting, that kind of stuff. The common aggregation, like taking the mean, the max, min, that kind of stuff is still there. So unless you're doing something very specific with pandas, I think you should be able to get by with using Dask as well. But there is a point where your data is just not big enough for that to actually make any effect, right? So.
What big means?
Pretty much, yeah. I mean, there's a trade-off because you have to start either a new thread or a new process to run the thing, right? And you have to transfer the data to the other process or whatever. So it can be a problem. Like, I mean, it says if you can get into RAM on your laptop, you probably just should use pandas directly, right? I mean, that's what they say, right? So. Something called distributed. Yeah. Let's see if I can go back. I don't know if this is a good protocol. Anyway, it's there. But I mean, this is a bit too in-depth for letting you know this script. I don't actually know how to use it, so I can't really tell you about that. All right. Since nobody else is presenting anything, I guess I'll do my second topic, which is about not actually working with data, but working with data. In other words, like managing your data, really. So, as you know, using Git with large files is not great, especially if they're binary files. I mean, Git doesn't really like it if you've got like a picture even that's like a megabyte or something like that. And then you have to update it multiple times, and you know, what ends up happening is that you save a copy of that picture every single time or every single commit, and then your Git clone becomes gigantic, so it takes a long time to clone and whatever. So there are, well, actually a lot of different things for getting out of that. I'm going to talk about two of them. So one of them is called git LFS, which was written by some people at GitHub for storing large files. So essentially what it does is it says, okay, well, you change some settings and it says, well, if you commit a file that's of this file type or if it's this size or something like that, then I'm going to not actually check that into Git. I'm going to say save a pointer thing that says I'm storing this large file. And then it stores the large file somewhere else. So, I mean, so for example, the example here is you install git LFS, then you say configure the thing here, which is git LFS install. And what that does is it installs some kind of hook into Git that says, whenever you commit something, I want to check those files to see if I should be tracking them myself. So what you do is you set git LFS track, say in this case, Photoshop files, and then save that attribute that you saved. And now when you add that file and commit it, it will be stored in LFS instead of in Git. So I'm going to look at the thing here. I have an example in, I don't remember what it's called. So So if we look in the model section here, this code is a code that does model visualization of global seismic models and stuff. And so I wanted to save all of the models along with it that came with or that's on the website for Iris. So, but as you can see, all of these are pretty large. I mean, some of them are like 36 megabytes, 40 megabytes. I mean, the smallest one is 25K, but most of them are around at least megabytes in size. So what you can do is, if I check my attributes here, I've told Git that anything that ends with GMT, anything that ends with grid, anything that ends with NC will go through LFS. So, I mean, I didn't write this line myself, but when I say git LFS track star.gmt, it will add this stuff automatically. And what it means is that the filter and the diffing and the merging will go through LFS. And so when you commit it, it'll go through the filter and LFS will start tracking it. And when you want to diff it, LFS will say, I'm going to diff it for you or whatever. And so for now, if you look at the files that are there, if I look at, I don't know if I can access this, but anyway. Well, it's not public, so I can't. But if you look at it on GitHub or GitLab, they understand LFS. So even though the file is not technically tracked by Git, it will show you the correct file there that's stored in LFS. So what happens is in here, I've got the thing, but also in my .git folder, in the actual repo part, there's an LFS folder which stores some temporary files and also a copy of all of those large files that it's got. So what happens is that when you clone a thing, you will clone your Git repository, and instead of actually all these NC files and GMT files, it'll be a file that says, go ask LFS for what this file actually is, basically. And so then LFS will download it to this temporary directory in here and make a copy in the actual place where it should be. And so this is great for medium-sized files, I guess, because then you don't have to worry about it, really. You clone it, you get just the repository part, which is hopefully just code or whatever, and it's not too big. And then LFS will download the big part, so then you can do whatever analysis you want to do on that. But you only have like 2 copies of the file, maybe. One for LFS in the temporary directory and one in the actual place. But if you got really, really big files, then LFS is a bit of a problem because you can't, or at least I haven't found a way to get it to only download what you want. I think there might be some settings for that, but I don't feel like going to work on that. So the other thing you can use is something called git annex. Yeah, basically, yeah. But I mean, it doesn't download every previous copy of it, right? Like if you checked it into Git, yeah. So if you checked it into Git, you get every single copy of it in your Git repository, and because it's binary, you would probably have a copy of every single thing because it wouldn't diff very well in the way that Git works. But with Git LFS, it will only download the one that you have a checkout of.
So if you were to do Git, it would download the one
Probably, but I mean, I'm only using it for binary files. So I don't know what it does for text. Generally, it sets it to be a binary file, so then you can't diff it in the same way as a text file, right?
If you wanted a previous version.
What?
If you wanted a previous version.
Yeah. So if you do like git checkout, head -1 or something, or then it would download that copy of that thing and then get it for you. So it will take care of keeping it in sync, but you're not really in charge of which copy gets downloaded. So I mean, if it needs to be downloaded, then they'll download it. If it needs to be deleted, I'm sure there's a cleanup thing, but you normally don't have to worry about it. It'll eventually garbage collector or something like that. So git annex is the other thing when you're working on really, really big stuff. So like I have a result from a simulation that's like 5 gigabytes. I don't want to download it. Well, one result is 5 gigabytes, but there are many results. So I don't want to download every single result to my laptop, for example, if I just want to try out some kind of calculation. I just want to download one of them. So git annex is a similar thing to git LFS. It's a bit more powerful, but it also means it's a bit more complicated to understand. And to be honest, I don't remember everything to use it, but the example is here. So if I look at my Git folder, now I've got an annex file, which has got a bunch of stuff. But anyway, or an annex directory, it's got a bunch of stuff. But as opposed to LFS, what you can do with git annex is you can be more specific about what you actually want to download. So if I look, the difference with LFS and git annex is that git annex will, instead of making another copy of the file, it will make a link or a symlink. So it'll be a symbolic link. So if I look at I haven't downloaded anything here, but this repository is a bunch of PDFs of some scanned stuff, which I never got around to finishing working on, but it's a bunch of PDFs of scanned stuff, and so every PDF is whatever size, 20 megabytes or something like that. And so you see the difference here is that instead of having another copy of it, what you have is you have a symlink. So this link points to somewhere in the git.git/annex hidden directory. And the name doesn't really matter, but so what you can do is that I can do git annex list or something like that. And it's kind of slow, but anyway.
Those names are very long.
Hmm?
Those names are very long.
Yes. Well, what it does is wants to do like content hashing or something like that. So it will, the way it gets saved is the default is like a 256 or SHA-256 hash of the file. So that way, if you've got multiple copies of the file, it will only save one copy of the thing in the actual stored directory. There's some workaround on Windows. There's direct mode as well. So I mean, there's stuff to get it working on Windows as well. So actually, I should look at info. So what you have with git annex is that I can set I don't have to anyway. So this is my laptop, but I can set a remote to say GitHub and a remote to another computer, and then I can give it an annex name. So if I look at the git annex info, I can see I've got a copy on USB drive, a copy on another computer, a copy on this laptop, and a copy on Google Drive, which kind of stopped working, but anyway. And I can look at my actual thing is that all of the files that are annexed are actually 10 gigabytes. And there are 952 files. But the point is that I can sort of track myself where all these files are. So, I mean, this information is not really important, but the important point is that I've got multiple repositories linked in git annex, and I can look at, say, git annex list, and I can see that this file 160th battalion.pdf is currently, according to what my git annex tracking info says, is currently on one computer called the forum. Actually, all of these files are on there. I can do something like annex get 160 something like that. And I can manually pull it. I don't know if this will work because I might have to connect to Google Drive or something. But anyway. And so this gives you a manual view of the things. But when you've got, say, all right, that's not going to work because it's going to connect to my computer that is not available online. But anyway. So this way, if you're working on like Cynet, which is the cluster for UofT or whatever, you can say add something to your git annex there, and then you have your copy on your like office computer, and you have your copy on your laptop, all tracked by git annex, and then you can say add the file on the cluster, and then fetch it on your office computer. And then if you sync everything along, this is not going to work, so I might as well cancel it. Do something like git annex sync, which also probably won't work, but anyway. If you do a sync, then you'll know that, oh, I've got a copy of it on my on the cluster, I've got a copy of it on my office computer, and I have no copy of it on my laptop. And I can say, you know, get it from the cluster or get it from the office computer because I'm closer and the connection is better or whatever. And that way you can sort of manually track where everything is. Or you can just say, you can set a setting that, you know, my office computer wants to download everything I add on the cluster. It will say, oh, I've added a bunch of files in the cluster. I'm going to just download all of them when I'm doing a sync. So, I mean, it's kind of like a more customizable LFS in that you can say, oh, on my laptop, I don't want to download everything, or on my office computer, I want to download everything that I've added or whatever. And then you can also manually or automatically track that you are or are not going to keep old copies or whatever, that kind of stuff. Anyway, since my battery's low, I can't really talk anymore. It's really not very useful. If you diff a binary file, you basically get like base64 encoded copy removed and base64 added. It doesn't really mean anything. I mean, if you understand the base64 version of your binary file, sure, but I don't think you do. So it just looks like very interesting. So yeah.
I'm guessing that the annex of the LFS use the hash for it. It's saying that it's different as opposed to showing all the ways that it's different. It's showing the problem.
Right. Yeah. I mean, it's not like it's going to tries to compact things by saying, you know, you changed only this line, and I can just store that diff or something like that. I mean, it doesn't technically do exactly that, but it can do that. But with Annex or LFS, it'll store just a single copy of whatever. Or, I mean, multiple copies if you made more than one commit. But, yeah. I mean, the cool thing about Git Annex is that it's got a bunch of different special remotes. So you can you can have your thing upload to like GitHub. Well, actually, you can't have it upload to GitHub because they don't support it, Annex. But you can have it sync to like your office computers, or you can have a special remote which would upload to like Google Drive or like Internet Archive or something if you're doing like humanities work or something like that you wanted to preserve, you know, like scanned books or something like that. You can have it automatically sync to Internet Archive or something along those lines. And then it should track all those things and be like, oh, you put the copy of this on Internet Archive. I can download it from there, or I can download it from your other computer if you prefer that, or, you know, I mean, you can set priorities and stuff, but it's still doing stuff.
Both of them, both LFS and Annex,
So GitHub supports LFS, but like the pricing is weird. It's like you have 1 GB limit, but it's some kind of weird like 1 GB download amount or something. I don't know what it is exactly. It's kind of odd. GitLab also supports Git LFS. So I mean, and that's in the, and then you're limited by whatever their full limit is. So like, no, yeah. So it was written by some GitHub employees, but so they could add. Basically, I think they were trying to go after like the creative side of things, where if you want to put in a bunch of like Photoshop files or whatever, but you don't want Git to be really bogged down by having to download, you know, 10 copies of your Photoshop file. I'm gonna disconnect this.
And I sent you a link to it.
Yeah, I just got it.
All right. Whoa. It's upside down. Okay, it's totally upside down. But cool. All right, so I'm gonna explain like 3 or 4 obscenely simple ways of working with large text files in Bash, because I do that. What is this? Cool. So let's say I've got like this large FASTA file. So in here in my home directory, which is a mess, there's this, which isn't that big, but let's pretend it's big. A useful way to peek into it is less, which will just open a snapshot of it. I know that's a mess, I'm sorry. But you can kind of scroll through it and we'll load it sequentially as you go. So this works for like massive files that are gigabytes upon gigabytes large. You're not going to overload your computer just by opening this up, or the server you're on. Less often defaults to wrapping things, which is annoying. So I like to use the capital S flag to prevent that. Why can't you see the left side of the screen? It says less, not S, I promise. If you add a capital N, you get line numbers too. Why, oh. so now you get line numbers, and this will turn off word wrapping, which is great and useful because that'll often mess up your data files. Another useful thing that a surprising number of people, including myself, don't know about is that cat will actually take multiple arguments. So if you want to concatenate two files, some people sometimes read that into Python, save it as a string, then combine the two. But you can literally just go, I don't know, let me make a copy of this. Call it 2, and then just, wait, what am I doing? Okay, so now I made a copy of that, and I want to stick them together. So instead of doing all that, you can just go cat, and then just the second file. Sorry, my screen blinks, it's annoying. And just combined.txt. And like, that'll do it. That will combine the two instantaneously. You can also use the append function, so I could go cat this, and then just append that with 2 greater thans instead of 1. Append that to the end of, I'm not going to hit tab because my screen will flash. And that will also, that'll append whatever I'm feeding from cat into that at the end of this file. So if you want to combine files, that's a really fast way to do them. The last thing I'm going to explain is split. So sometimes if you've got like a parallel thing on your server, which most people do, and you want to, you've got this huge text file and you want to run analysis on it, you don't want to just sit there while your thingy goes through the file bit by bit. You can actually split the file up into lines. So how do I do this in a way that's, okay, 1 sec. 4, no. Okay, so let's look at this file here. It's got 47 lines. I can actually split this into files that are, let's say, it's not an even number, which is annoying, 20 lines each, and then the last one will just have the leftovers using split, L20, snip, seek, and if I check here, these 3, I didn't give it a name, so just went with X. They're just the file split up evenly, so you'll notice these 2 are the same size, and then the last one just has the leftovers because it wasn't multiple of 20. And then you can use parallel. So I don't have new parallel, so I'd use parallel, J3, what have you. And you can run the same, like assuming your files are conducive to this sort of thing. You can run the same thing in parallel over like one single data file, so splitting it up and then combine your results at the end of the day. And that's pretty much all I have. Cool. Bash is great. Thank you.
One piece